Jupiter's moon Ganymede is the largest moon in the solar system. Indeed, it is actually larger than the planet Mercury. A strange moon that superficially resembles our own, its surface is very different in composition, but it's also larger. But also, seemingly paradoxically, it actually has lower surface gravity than the planet Mercury, but that's because it's less dense. It orbits Jupiter about once a week and is composed of roughly equal parts water and rock, with the water component being ice, but also a suspected subsurface ocean beneath that is believed to contain more water than Earth's oceans collectively contain. This salty ocean is thought to be weird, in that it may consist of several oceans, stacked one on top of each other, separated by phases of ice and layers. An unusual thing to consider here is that if those oceans each harbor life, each ocean could be hosting radically different life from the other layers. Different conditions produce different evolutionary processes, though it's difficult to see how a separate abiogenesis could occur in each layer, since only the lowest ocean would be in contact with rock, if that lowest layer is not insulated with more ice, because of the probable need for hydrothermal vents to provide nutrients and an environment where abiogenesis could occur. But Ganymede could also be completely sterile, even though it is as ancient as most of the rest of the solar system. Chances are we will never know, as Ganymede's icy crust is over 95 miles thick, and does not appear to have any active plumes right now, though it's thought that this might have occurred in the past, not unlike those of Enceladus and Europa that are currently active. But Ganymede is unusually well preserved in a certain way, providing a window into an earlier period of the solar system's history. More on that in a bit. Ganymede has a very strange feature. It actually has its own magnetic field from a molten interior and convective dynamo, helped by the gravitational flexing of Jupiter creating heat along with natural radioactive decay. But it leads to an odd situation of Ganymede's magnetic field interacting constantly with a much stronger magnetic field of Jupiter, leading to Ganymede having auroras in its very thin atmosphere. The surface of Ganymede falls into two types. One consists of lighter regions featuring extensive grooves and ridges, the origin of which is a mystery, and darker cratered terrain, all about 4 billion years old. But Ganymede also has another very interesting possibility. It could be a gigantic dark matter detector, and it won't be difficult to determine if it is with future Jupiter missions. The problem is that we still don't know what dark matter is and what its properties are. Typically, it's seen as a weakly interacting massive particle, like a neutrino, just vastly more massive overall, that should interact with matter only occasionally as neutrinos do. Except we've never seen such an unexplained interaction in our neutrino detectors, meaning that either our detectors can't pick up the dark matter interactions due to wrong equipment, or the particle nature of dark matter isn't quite right. But there's still plenty of room for other hypotheses regarding dark matter, and one model of it says that it could take the form of an object with the mass of a small asteroid. But for the most part, these dark matter asteroids would just pass through solid objects without interacting. But if you had a detector the size of Ganymede, you should see a very rare interaction that should form a distinctive type of crater. And given that Ganymede's surface is 4 billion years old, it's a preserved relic surface for the solar system with a unique attribute. There has been a lot of time for such an interaction to occur. This is based on the work of William DeRocco at the University of Maryland, linked to his paper in the description below. And his calculations show that a dark matter asteroid would penetrate Ganymede much deeper than a normal asteroid would, and would reach the subsurface ocean below, which should bring up distinctive minerals from that ocean that should be detectable by Europa Clipper or the JUICE spacecraft when they begin operations. The craters are expected to be small, isolated from other geologic features, and if radar is used, it should be visible as a column of melted and recrystallized ice leading all the way down to the ocean below. Interestingly, if this model is correct, it could explain why we haven't detected dark matter yet. If dark matter masses are small and not very interactive, and somewhat scarce in our context, then we simply do not have a detector here on Earth that would pick one up. You really need something the size of a moon to see anything like this. And even then, it's not clear what such an interaction would do to Earth, or how deep in the Earth the interaction would be, and what evidence would be left. But Ganymede is uniquely suited for this in that it's ice with a subsurface ocean, and also a surface that has not changed much in 4 billion years. It's also worth noting that this kind of cratering, if cratering is really the right word, more like punching a hole in it and filling it back up and refreezing, would actually leave 2 scars on Ganymede, an entrance and an exit wound, which if you could find both of them might serve to corroborate that a feature fitting this prediction actually is a dark matter mass. But using Ganymede as a detector isn't the only idea in regards to searching solar system objects for clues to the nature of dark matter. There's also asteroids. The Milky Way is surrounded by what is termed the dark matter halo. It encompasses the galaxy and ultimately prevents it from flying apart due to its rotation. As the solar system orbits the galactic center, and indeed through its own proper motion, it should encounter a kind of dark matter wind as it moves, like a rocket punching through an atmosphere. If the particle nature of dark matter is correct, it may be that it works like moving through the air. You hit turbulence when you hit pockets of denser air, and dark matter may work like that as well. That means we may encounter this dark matter turbulence from time to time. It might be that when we encounter such turbulence, which is termed an overdensity, it may make dark matter easier to detect, and the reason we're not seeing it right now is because we're in a kind of local calm. But it might also mean that if we are in an overdensity zone, then dark matter is darker and harder to detect than we realized, even though we already knew it was hard to detect. This is a vexing issue because to understand dark matter in this context, we need to know how much of it surrounds us locally. But since we already can't measure it apparently, then we need some other way to test these ideas. And that's where the asteroids come in. And in particular, one asteroid stands out because we've studied it to death. It's Bennu, the asteroid that was recently in the news again when it was found to contain sugars and all of the building blocks of RNA. To go to Bennu to get the samples that found the sugars, an unprecedented amount of tracking data was taken for Bennu, largely by the OSIRIS-REx spacecraft that took the samples. The resolution is so good it might be enough to try to tease out subtle effects of the presence of dark matter that might help answer some of these questions. Basically, you go back to Newton with this technique. If you see motion you can't account for, then that's your detection, because we can very precisely use Newton's laws and things like relativity and gravity tugging and all of that to derive exactly how an asteroid's orbit should behave. And if you see anything outside of that, you must account for it. And that can tell you how much dark matter is present around the asteroid, even if it doesn't tell you what the dark matter actually is. You can also do this with planets as well. So the hope is eventually to use all these orbiting objects to someday be able to construct a map of the distribution of dark matter in the solar system, and even how that changes over time, though that will take centuries to thousands of years. Interestingly, this mapping might even yield a prediction of when Earth will pass through a denser blob of dark matter, which should increase the chances of detection and help us determine exactly what this stuff is. Here, I have to bring up something rather delightfully strange. So this comes from Starkman and colleagues in 2021, again, link below. Again, if dark matter clumps and isn't just a spray of particles everywhere like neutrinos, things get weird. The researchers detailed that such a class of clumped dark matter, if dense enough, again, if we pass through a dense area of it, and you had the conditions just right, such as in a lightning-producing thunderstorm, the effect would be to create a lightning seed with a single leader instead of multiple ones, which is sometimes thousands all strung together, like in a normal lightning strike. This would result in very straight, like an actual straight line, bolts of lightning. This has never been observed conclusively. The straightest lightning bolt ever recorded probably isn't straight enough for it. But we've only been scientifically recording lightning for a few hundred years, so there is room for this. But lightning isn't unique to Earth. Venus probably has it, and Jupiter certainly does, which means you could search Jupiter for evidence of straight lightning bolts if it passes inside of a dark matter clump. Dark matter storms, strange indeed. With the asteroids, however, there is another possibility. It was also hypothesized that they could be used to detect a fifth force of nature. This, however, was not observed with Bennu dataset, which constrains how strong such a force could be, if it exists, and is linked to dark matter that involves ultralight particles. If nothing is discovered, this allows scientists to rule out certain hypotheses regarding the nature of dark matter. But it's also possible that other dark matter research may beat the asteroids to the punch. Just last month, it was announced that a new analysis of a large dataset collected by the Fermi Gamma Ray Space Telescope over 15 years show a glow of high-energy gamma rays surrounding the Milky Way that have no known source, but seem to be in a halo as we believe dark matter to be, and that may constitute the first direct detection of dark matter. Researchers at the University of Tokyo suspect this may be the result of dark matter particles colliding and annihilating, and doing so at an energy level corresponding to the galactic dark matter halo. This bolsters other rather inconclusive evidence of increased unexplained gamma ray emissions from the galactic center and excess, where dark matter should be at its densest. But there are a lot more sources for gamma rays at the galactic center than the rest of the galaxy, so that was a problem. But the halo is not so packed with those sources. So if this new research holds, it would almost certainly nail a particle nature for dark matter, and tell the rest of science where we need to be looking for dark matter to learn more. But we may finally be further along now in the hunt for what dark matter actually is and how to finally identify it. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently pondering the horror that is the anti-LeBaron. Physics does not permit one from creating a 1984 Chrysler LeBaron made of antimatter and getting it close to a normal matter car and the two mutually annihilating. Be careful, Lamborghini. You may be faster than a LeBaron, but only if you survive being parked next to one. And be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.